Hello everyone, welcome to Mechanical Engineering Design and Innovation course. Myself Dr. P. Rajkumar, Assistant Professor, Department of Mechanical Engineering. The topic for today's discussion is selection of shapes and a case study on the selection of the materials and shapes. So the aim of the present session is to make you to understand the selection of shapes and materials and a case study on it. At the end of this session, you will be able to understand how to select a material based on the concept of shapes. And we will be discussing a case study. So based on that case study, you will gain the knowledge to select the different materials based on the shape. So let's start the selection of materials and shapes. We know that the tie already told you, tie is a structural member which is used to carry or majorly designed to carry the tensile loads. Similarly, beams are designed to carry bending moments. Shafts are designed to carry torques. Columns are designed to carry compressive axial loads. For all these kinds of loads like tensile load, bending load or torques and compressive load, if I consider for example axial tension, then all the cross sections with the same area will carry the same load, because the load sigma is equal to F by A. If A, the cross section area is same, then the load also will be same. So to carry this axial tension or to select a material based on the shape, here to design, or if the member is subjecting only to the axial tension, then shape is not a concern while selecting the material. Let's see the another loading criteria, that is the bending stress. We know that the beams with hollow or box or I sections are better than solid sections of the same cross sectional area, because we know that the sigma B is equal to M by Z, where sigma B indicates bending stress, M is equal to bending moment, Z is section modulus. Here the sigma B, the strength is depending on the cross section. That means even though the area is same, it is depending on the cross section. So this is one criteria where we have to select the material based on the shape or based on the cross section. Now let's consider the torsion. So circular tubes are more efficient than either solid sections or I sections. So here also the cross section matters, and while choosing the material. So here axial tension shape is not a concern, but whereas in the bending as well as the torsion, the shape or the cross section is matters while selecting the material. So here, whenever, for example, whatever cases here we discussed, all those cases are independent of the material. But you just imagine a situation where you have two types of different designs as well as you have two material selection options. So you have to design, as a design engineer, you have to select the best design by working on the suitable materials, shapes and the design combinations. So while working on that, you have to consider the shape factor into account. So what do you mean by shape factor? So the shape factor is nothing but it is a factor which characterizes the structural efficiency of a section shape and the material usage. That means it is a factor which will tell us the efficiency, which will indicate the efficiency of a section of a shape as well as the material usage. For example, for this loading condition, if you use this cross section, you will get one shape factor. For the same loading condition, if you use different cross section, then you will get the different shape factor. So like that, the shape factor will be different for the different cross section, and based on that values you have to select the optimum material for your design or for your component. So let's see in detail what is this shape factor and all. Here while choosing the shape, while shape in the sense you have to consider the shape factors for bending as well as the twisting, because there is no concept for selecting the shape factor for the axial tension. And the micro shape factors also we have to consider, and indices, material indices also we have to consider. Then we have to do the material selection based on this material selection we have to do based on the shapes. So here let's see the what do you mean by shape factor for elastic bending. Here the E indicates elastic, B indicates bending. Okay. So it is defined as the ratio of the bending stiffness of a shaped section to the bending stiffness of a solid square section. For example, the shaped section may be I section or C section or T section. Then with respect to S naught, that means the stiffness of solid square section, we are calculating the stiffness values, and that's by substituting all these I values we will get 12I by A square. A is the cross section area as well as the I is the second moment of area. By substituting the values in this equation, we will get the shape factor for the elastic bending. So let's see, we know that the design will be considered in the two modes. One is the based on the stiffness approach as well as the strength approach. So the stiffness approach for bending the whatever material index, we have derived that I am indicating with the M1. In the stiffness approach, for a torsion loading, the material indicated with M2 material index. For strength approach, in a bending case it is M3. For strength approach, for a torsion loading it is M4. And these are the corresponding elastic bending shape factors for different cross sections. So you can understood here the shape factor is constant irrespective of the size of the cross section, even though it is small, medium or large. For a rectangular cross section for elastic bending, the shape factor is 2. That's all. It is common. That means the shape factor, it won't depend on the size of the cross section. So let's see the one case study, the forks for a racing bicycle. So how to choose the a material for this forks? So I told you in the previous session itself, like how to select a material. First thing we have to do is we have to design requirements, we have to find out. So what is the function of that forks, and what are the constraints we are having while designing the forks, and what is the objective of that forks, and what are the free variables we are having. So the function of the fork is it should act like the bicycle forks, and the constraints must not fail under design loads. That means because the rider weight as well as the road reactions and the impact load, sometimes it will act on this frame. So whenever these kind of loads are acting, this frame should not bend or they should not fail. So that means they should withstand that applied design loads. So what is the objectives of this fork? It should have minimum mass. So that is my objective. And what are the free variables? We have the option to vary the choice of material as well as we can vary the section shape. And in the previous session itself, we have seen how to derive the material index. And in the previous slide, I told you M3. M3 means for a strength criteria in a bending load, this is the material index value. So the same value I have taken here. M3 indicates with respect to strength criteria, with respect to strength criteria for a bending load, this is the material index value. So based on this, I have to choose the material. So if you see, these are the different materials that we consider to select a material for the forks. So what is its strength, what is its density, and what is its shape factor, and what is the material index M3 value. So what is this M3 value? Okay, this is the M3 value. So we know that the maximum, whatever the material with maximum M3 value, that will be the best material for your forks. If you see here the M3 maximum for CFRP, so we can say CFRP is the best material to fabricate these forks. But if you say cost is your constraint, then you have to go for the next best material, titanium. It is also costly. So next best material, then you have to go to 59, bamboo. So you have a concern here with respect to strength, because strength is less. Where is 300 to 450, where is 80 to 160. So strength here it is a constraint. So what is the next? Steel or aluminum. So both are having same. So either you can choose either steel or aluminum. If you have cost constraints, you can choose any of this, steel or aluminum, or you can choose CFRP based on this material index. So in the previous session we have seen how to select a material for your table legs. Now for the same table legs with respect to or by considering the cross section of this table leg, we will find out the suitable material for it. So the tubular cross section here I am considering, and for this tubular cross section the material index is given by this value, and the cross section area is 2 pi r into thickness, and this is the moment of inertia, and since r radius of this tubular leg is the free variable, so I am taking r, I am deriving this in terms of r, and I have to select this now material with respect to shape as well as the material. So instantly what I am considering? I am considering my solid leg with the factor, shape factor is equal to 1. So you can see here the horizontal line here, horizontal 1, which is like this black line is 1. Okay. So for instance, because in earlier studies I told CFRP is the best material, so I am starting with the CFRP. So what is this chart? E to the rho. I know that from the previous analysis I know CFRP is the best material, so I am starting the, I am verifying whether that CFRP is best material with respect to by considering the shape also. So I have chosen the CFRP and I have drawn one horizontal line. So with respect to G value and your second moment of area, that means the chart of E to the I am selecting with respect to the values of E to the I am selecting one point here, and from that point I have drawn one vertical line here, and here I am selecting the shape factor. Pi b is equal to 100, pi b is equal to 10, 1. So 1 means it indicates the solid section. Okay. So for this solid section, what is the performance? This chart, the standard area to the density, it will give you the performance chart. This chart we will call material chart, this chart we will call constraints one, this one will call shape, here it is performance. So if I choose the CFRP material and for a solid cross section, I will get the performance here in this range between 10 power minus 3 to 10 power 4 minus 4. Let us consider for the same GFRP with respect to tubular cross section. So I have taken GFRP here from this vertical line, here the tubular cross section which is having the shape factor of 10. So I have taken 10, and from here if I draw horizontal line, my performance is getting reduced, because if I take the tubular cross section, it won't withstand for the applied loads, that is why its performance is decreasing. Okay. If I consider the solid legs, then whatever material I have chosen GFRP, that can be considered as the best material. Okay. Like this, using these 4 charts, we have to find out we have to select a material based on the shape and its function. So for this particular table legs application, GFRP. If cost is constraints, then we have to go for the wood or other materials. So these are the different textbooks for your further learning. Thank you.